Thank you for the introduction. So an ongoing problem in virtual reality is providing accurate dynamic haptic feedback, which correlates with the user's visual perception. So past research of this problem has explored haptic gloves, encounter-type haptics, electrical stimulation, and pseudo-haptics, just to name a few possibilities. But these devices are often complex. They approximate haptic feedback, and they are unable to prevent the user's hand from passing through the physical object, the virtual object, sorry. But in VR, we often see controllers with pointers or hand tracking and intangible direct touch interfaces to enable dynamic interface interaction. However, these generally lack tactile feedback, so how can we provide accurate tactile feedback for a virtual interface that correlates with its dynamic visual representation without these limitations? So we propose a solution to this problem utilizing haptic retargeting illusions to enable a single physical button to provide accurate tactile feedback for many virtual buttons on a handheld interface. So just as an example, given a Vive controller with a single physical button on it, we can extend it to have 9 buttons or however many buttons we want, all arranged in a dynamic interface. And to support this bimanual interaction, we extend existing haptic retargeting algorithms and propose a new haptic retargeting technique, which we named interface warp. So this operates independently or in combination with other techniques. And we explored how these haptic retargeting techniques and the introduction of bimanual interaction affect task performance, perceived manipulation, and presence for this type of remapped interface interaction. So hand tracking technologies can provide natural interactions with dynamic interfaces in virtual reality. However, these interfaces are often intangible. Your hand can pass through the interface, and they lack the tactile feedback of a physical interface. This is an important limitation, as it's been shown that passive haptic feedback significantly increases task performance for user interface interaction. And there has also been some work on making a physical interface dynamic using pneumatics to enable buttons as required. But this type of interface requires a prior understanding of the possible layouts you might want, and it has a limited operating surface area. But in this work, we specifically focus on asymmetric bimanual interaction, where the non-dominant hand holds the target object and provides a frame of reference within which the dominant hand performs its actions. The non-dominant hand also provides stability to the object, and it generally performs less precise movements than the dominant hand. It's been shown that with selection tasks, they perform significantly faster when interacting with a handheld passive haptic as opposed to a fixed passive haptic. And we see this type of asymmetric bimanual interaction in many modern devices such as mobile phones and tablets. Visual haptic illusions leverage the dominance of visual sensory input over touch perception by manipulating what's seen to alter what the user feels. And it's been shown that humans tend to perceive a visual shape rather than a tactile shape when you introduce a conflict between these two. These illusions have been leveraged in virtual reality and haptics in papers or examples such as redirected walking, redirected touching. It's been used to improve shape display performance and also ergonomic optimization, just to name some applications. And redirected touching is particularly relevant to this work, as it enables the user to perceive virtual objects and to have a different shape or position or orientation to the physical haptic used to represent them. But this work specifically extends on haptic retargeting, which is the visual haptic illusion which enables reuse of passive haptics in virtual reality. It consists of 3 types of warp: body, world, and hybrid warp. Body warp being a spatial warp applied to the user's virtual hand as they reach for a target. World warp being a rotational gain, and hybrid warp, which combines these two. And it was shown that these retargeting techniques provide significantly higher haptic presence compared to a wand with vibration feedback. And the body warp technique had significantly more user corrections than the world and hybrid warp. It's also been applied to the sparse haptic proxy system, which is a similar algorithm and maps surfaces to panels assembled in a large hemisphere. And that it applies gaze and hand tracking is used to identify the user's intended target and redirect accordingly. So for our system, we implemented a new type of warp, which we labelled interface warp. So this technique is applied individually or in combination with other warp techniques. And it's based on the body warp algorithm from the haptic retargeting work. So instead of applying the warp to the user's hand to guide their physical hand, the warp is applied inversely to the physical interface. To the virtual interface. And this moves the virtual interface to match the physical and virtual target buttons as the hand approaches. We also added support to the interface and body warp algorithms for asymmetric bimanual interaction. To do this, the offset calculations are performed within the local space of the physical interface, and this enables the interface to move in space without affecting the relationship between the target position, the warp origin, and the interface. So we conducted an exploratory user study to evaluate our system and determine if there was a measurable effect on haptic retargeting techniques and the bimanual haptic retargeting on task performance, perceived manipulation, and presence. And we hypothesized that both the mode and the warp would have a measurable effect on these variables. We recruited 22 participants for the study, 15 male, 7 female, all of which were right-handed and had normal or corrected to normal vision. The study included an initial practice condition plus 6 experimental conditions, and these conditions consisted of the 2 modes with 3 warp techniques for each mode, and the 2 modes being unimanual, where the physical haptic was attached to the desk, bimanual, where they held it in their non-dominant hand, and a body interface warp and combined, which was just the 2 combined together, similar to the hybrid warp. For the procedure of the study, the participants interacted with a physical interface consisting of a board with 2 physical 2 centimetre by 2 centimetre tactile buttons. 1 button was centred on the board and 1 is centred on the lower edge of the board, and that provides the reset and warp origin for the interactions. The interface is tracked using a Vive tracker, and the user's hands are tracked using a Leap Motion mounted on the Vive Pro head-mounted display. For each condition, participants first calibrated the interface to bring the Vive space and the Leap tracking spaces together. Next, they performed the main conditions. So they pressed 9 virtual buttons arranged in a 3x3 pattern centered on the physical button. And the buttons were pressed in a random order with a press of the reset button in between each press. After each condition, participants completed the Whitmer and Singer presence questionnaire with additional questions on perceived manipulation of their hand and interface. So some results from our analysis. Task performance was measured through completion time and errors. So errors were counted by the supervising researcher, and any instance where the participant missed the button and hit the board instead was counted as an error. And our analysis showed a significant effect of warp on response time, with the combined warp being significantly faster than the body warp. And we also showed a significant effect of warp on errors, with the combined warp and interface warp having significantly fewer errors than the body warp. Perceived manipulation was measured on a 7-point Likert scale between no manipulation and extreme manipulation. We showed a significant effect of warp on perceived manipulation of the virtual interface, with the body warp being significantly less noticeable than the other types, and no measurable effect of the mode was found, that's the bimanual or unimanual, on the manipulation of the interface or the hand. So while the analysis shows the interface warp provides improved task performance, it also shows that the interface warp is significantly more noticeable than the body warp. And our analysis didn't find any significance in the Whitmer and Singer presence questionnaires or the preferences of individual participants. So this system and study have several limitations which we feel require future work. Firstly, the tasks were all performed in a scripted order. So the sparse haptic proxy work used a target prediction, which would enable you to have dynamic interactions with your choice of button rather than being told which one to press. And like similar research, our system also utilises an intermediary reset step, which interrupts the natural interaction, so further work is needed to eliminate or minimises the need for this step. And in this study, we also didn't require the user to actively move around the physical haptic or around the environment. So the warp techniques were only really tested while the user was sitting stationary, but they were able to move the haptic however they wanted. So further work is needed to understand how the system performs under more extreme movements, like locomotion around the room. And the interface of warp could also be modified to have some translational gain or apply it during blindness periods, like change blindness, to potentially make it less noticeable. So to summarise, we propose a system which provides accurate tactile feedback for dynamic interface in virtual reality. The system leverages visuo-haptic illusions to enable one physical button to represent several or a variable number of virtual buttons. We presented a new warp technique which can be applied to reduce the amount of body warp necessary, and while it was shown to be more noticeable than body warp, is also shown to reduce fewer errors. And combining these two is also shown to reduce the response time. Thank you for listening, and are there any questions?
If anyone has any questions, you can just come to the microphone here in the aisle. We have time for maybe one or two questions. I'll get started. You mentioned that haptic retargeting provides haptic presence. How is that different from regular presence, and how is it measured?
It was measured in the Whitman-Singer presence questionnaire. I don't recall the exact question. I think it's to do with like how you experience the environment. So do you feel something when you touch things? Do your hands pass through it and things like that?